Hey folks, Ms. Gosling here. In this video, you are going to learn about ohmic and non-ohmic resistors. By the end of the video, you will be able to differentiate between ohmic and non-ohmic resistors. And you will also be able to solve problems involving non-ohmic resistors, because so far we've really only looked at ohmic resistors. So let's go ahead and get started. So the first thing I want to do is compare and contrast the resistors that we've used in class with another object that has resistance, which is a light bulb. So the resistors we have in class, when we put them in a circuit, what we see is that they heat up, and that's really the only physical change that we notice. So there's nothing making sound or lighting up or doing anything else that's very fun. Light bulbs, on the other hand, generate both heat and light. So the effect of the electric circuit on the light bulb is a little bit different than the effect of the circuit on the resistor. And we're going to see how that difference affects the resistance of each of these two objects. So with resistors, when you did your lab, you were able to generate a graph of current versus voltage. Here I have a graph of voltage versus current instead, because this is actually what our graphs will usually look like. So our graph, the graph that you developed, looked a lot like this graph here. You had a straight line, and the slope of the line was the resistance of your resistor. Or in your lab, it was 1 over the resistance, but since we've flipped our y and our x, here the slope is our resistance. So the key takeaway here is that ohmic resistors have a direct relationship between current and voltage. So the relationship between the current and the voltage in an ohmic resistor is linear. And thinking back to Ohm's law, V equals IR, this linear relationship between V and I, means that the resistance is constant. So no matter how much voltage I run through, no matter how much current I run through a regular resistor, the resistance of that resistor will remain constant. Our non-ohmic resistors, on the other hand, do not have a linear relationship between V and I. So again, non-ohmic resistors have a non-linear relationship between V and I, and we can see that here in our graph, which has a bit of an almost exponential look to it. Though I'm not going to use the word exponential because we don't actually know that this follows an exponential, without the line of best fit and the equation for the line of best fit, we can't actually say that this is, in fact, exponential. However, you can tell that it is clearly not a straight line. We've got a little bit of a more shallow curve here, and then our curve gets steeper closer to the top. So the key thing to know is that V equals IR is still true for our non-ohmic resistors, but the resistance of the resistor is not constant. So what that means is that the resistance of my light bulb at a current of 0.02 amps is different from its resistance at 0.05 amps because the V versus I relationship is different. So what we are going to do in this video is actually go through how to find the resistance of our light bulb at different, using these graphs at different voltages and different currents. But before we do that, I want to really quickly introduce you to a non-exhaustive list of non-ohmic resistors and the graphs that go with them. So first of all, we've already talked about the humble incandescent light bulb, the filament lamp in IB speak, and the classic current versus voltage graph for the light bulb looks like this. So we're kind of curving and getting steeper near 0 and then shallower the farther we get away from a voltage of 0 volts. Next, we have gas discharge tubes, and the most well-known version of a gas discharge tube is in fact the fluorescent light bulb. But any gas tube that we use to generate light is a good example of a gas discharge tube. Another good example of a non-ohmic resistor is something called a thermistor, which is a temperature-dependent component in a circuit. And you can see here that the relationship between V and I is so significantly different that we're actually graphing the logarithm of V against I, not V itself against I. So this linear relationship is, it looks like this relationship is linear. It really, really isn't, because again, we are graphing the log of V against I, not V itself against I. The next thing we have are our two diodes. So we have our thermionic diode and our semiconductor diode. And for both of these, you can again see we have a nonlinear relationship between our voltage and our current. Finally, in the bottom corner, I have an example of what an ohmic conductor's graph should look like. So what we should have is a clear, straight line with no breaks between it from the lowest negative voltage to the highest positive voltage. So now let's go ahead and go through an example problem. So this graph on the left shows the current versus the voltage for a non-ohmic conductor. And what I'm going to go ahead and do is find the resistance at a voltage of 2 volts. And to do that, I'm going to start by going over on my x-axis to 2 volts. So 0, 1, and 2. And then from there, I'm going to go up to my line and mark the point that is at 2 volts. Going over to my y-axis, I can see that my current at 2 volts is about 1.5 amps. So at 2 volts, my voltage is obviously 2 volts. My current is 1.5 amps. Plugging that into Ohm's law, V equals IR, I can, which I'm going to now, first, before plugging in numbers, solve for R. I get that my resistance is my voltage over my current, or 2 volts over 1.5 amps, giving me a resistance of 1.3 ohms at 2 volts. Now, if I was to do the same thing at 1 volt, I would get a different resistance. So looking over at 1 volt, I can see that my voltage is 1 volt and my current is 1 amp. So that means that my resistance, V over I, is 1 over 1, or 1 ohm. So at 2 volts, my resistance in my non-ohmic conductor here is higher than its resistance at 1 volt. So you can see here that we have that changing resistance, which affects that voltage and current relationship. And because of this nonlinear relationship, usually when we are solving these non-ohmic resistor problems, we are actually going to be using the graph, or you are almost always going to have a graph, and you are going to use that graph to figure out your voltage and current and use that to calculate resistance. So with that, let's go ahead and talk takeaways. First of all, not all resistors have a linear relationship between voltage and current. However, we can still use Ohm's law to solve problems involving non-ohmic resistors, as long as we have a graph of their current versus voltage characteristics that we can use to determine their resistance at any given point. So with that, it is your turn to solve some problems. Best of luck and happy solving.